we'll continuing to talk about Capri behavior. I think next time we'll talk about rates of flow, but for now we're still talking about what happens in the first 2 months, drops into the subsurface and goes somewhere. We don't know anything about the rates at which it does that, but we can understand this based on what we've talked about so far. So these are just some animations that kind of epitomize, if you like, what we're talking about. You'll see that, say, I put them in looping mode, so the top right-hand one is just, you could think of it as a NAPL sinking down. The pore space was originally filled with air. The NAPL takes up that pore space, squeezes out the air, and maybe not all of it, but a large fraction of it. The gray parts are the grains that define the pore throats within it. And the other one, the bottom one, is showing a rising material just slowly filling the pore space. And so we notice in these that this would be, say, the top right-hand one would be under a prescribed pressure that's driving it in there. And so when we do this experiment, we're not interested in the early parts of it when it's only invaded slightly. We wait for it to become an equilibrium saturation. So on the red one on the right-hand side, it's quite long actually, it's going to start up again. I'm going to start it again. So initially it's completely dry, and then you increase the pressure of the red fluid and it slowly invades. It takes some time to invade, but once it's completely invaded the structure as much as it can, that is the saturation at that particular Capri pressure, and that is part of our curve that we were drawing yesterday, the Capri pressure versus saturation curves. And so that's exactly what we're interested in. If now for the red one we took and increased the pressure, it would look exactly the same as it did at the end, but there would be a little more red fluid in there, because under higher saturation, more red fluid would be pushed into the system. That's all. And so that's really what we're trying to do. The top one, top left-hand one, is kind of horizontal flow, and it's just a fluid that's being flowed in from the left-hand side. And actually, these are all figures from, or movies from, a company called Ingrain, which I think got brought out by Schlumberger or Halliburton. And the idea was that when you're drilling a well in gas shales, you'd like to know what the Capri pressure versus saturation curve is and the permeability. It's tough to get a sample, so what you can do is you can collect the drill chips as they come back up the borehole onto the surface as they're removed from the well. Tiny little chips, probably the size of my finger. You X-ray CT them to find out what the pore structure is. You get a map a bit like this gray thing in the background which defines the pore throat structure, and then you run a model to be able to see how much fluid goes into different places in that model, and you can reconstruct the Capri pressure curves and the relative permeability saturation curves, which we haven't talked about yet, directly from that information. You don't need to run an experiment. You can't scan it, you get the geometry, you run a numerical model on it, and it gives you that answer. So that's why it's kind of interesting. So that's what we will think about today. So what we'll do today is we'll talk again, just for a change, about Capri behavior. I'll get my thing working. I'll use my blunt object. We'll go through a quick recap using some stuff I did a few years ago that you don't have, but it explains things quite nicely, I think. And then we'll answer this one question. This is kind of the essence of the question we answer. So how deep does the NAPL go? Does it stop at anything? It seems to stop at Capri barriers. How good do those Capri barriers have to be to stop it? If the Capri barriers aren't there, will it finally run out and stop migrating downwards? Or will it just keep on going to the center of the Earth? So that's kind of the question that we'd like to ask in a broad way. And of course that will help inform us exactly why we get this specific architecture. We've already talked about this. We talked about the method to do this. I think we talked about a vanometer in this class as well already. And so we'll talk about when invasion occurs and what the architecture of that stacked red deposit might be. So figures that we've seen before, but we're going to actually kind of walk our way through that. So for this, I had this summary slide, which I'm quite pleased about. not overly pleased, but this kind of encapsulates lots of the stuff that we've talked about so far. So I don't know, you don't have this, you're welcome to take pictures of it as you wish, or just to draw the essence, or just listen to what we're talking about. They're all concepts that we've talked about already. And so the idea is that we're curious about this architecture, and we want to know why it forms this smear, why it forms these lenses, why it might be stopped by a Capri barrier, and more importantly, what are the physical characteristics of those that we can measure that would be able to allow us to tell how they would work that way. And so we can look at things in macro scale like this, or we can look at a small portion of the aquifer in micro scale. And this is a picture on the bottom of two bead packs. I could actually point to it here. Right. And this is a coarse bead pack, and this is a fine grained bead pack. And you see that this invading fluid has been stopped as it gets into the fine bead pack. You know why. You know because the capillaries are relatively small, and therefore the pressure or height of material you have to apply to push it in here is quite high. And if this height isn't large enough here, then it won't go in. But part of this bead pack also must have some portions which are perhaps more open than others, and it's allowed this little finger to go through here. And it describes quite nicely really what's going on in these individual fine-grained lenses that are acting as support Capri barriers for the stuff that's coming down. It's pooling on top of it, and then it's flowing off the side until it hits another one and cascading off that. So it's kind of a cool structure. We can think of this in terms of these concepts of their capillary rise, in terms of the height rise in a tube or the height rise in a fracture between parallel plates. And that would be perhaps useful for us to think about this. But one easier way to do it is to think of our REV, which I guess I would be able to draw on here. We talked about representative elemental volumes. And so we take a volume and we look at the properties of that volume, just like the little cubes we saw in the animations. And if we do that for the animations, we end up with a little curve that looks like this. So we're now looking at Capri pressure versus saturation curves. We define a Capri pressure, which is in essence the difference between the pressure that's measured right at this point in the fluid 1 and this point in fluid 2. They're different because there's a curvature in it. The larger that curvature, the larger the difference in these Capri pressures is. And this is defined as the Capri in the non-wetting fluid. If this is water here, then this is the wetting fluid. So the air would be the non-wetting fluid, and the water would be the wetting fluid, if you can see that. Yeah, hopefully you can see that. And we use this concept of the difference between those two pressures to be able to characterize exactly what this is. And so this is the difference in those two pressures. So if we took the sample that we had last time and we applied a pressure to the outside and the initial pressure in the middle is 0, then the Capri pressure will just be the magnitude of the overpressure that we're applying to force it into that sample. And as we apply a bigger and bigger pressure, we'll force the NAPL into the sample as we increase the Capri pressure, and it will change the saturation. Initially at this point it would be 100% water saturated, and as we increase the pressure it would now be at this point this percent saturated with an NAPL, which looks like it's about 70%, and this percent saturated still with water, which looks like it's about 30%. And so that's just a way that we can describe how this behavior changes as we change the driving pressure into this space. It will look very similar. It will look red all the time because you can't really see the part of it which is the clear water which is embedded in that. And clearly, once you get a bit of red stuff in there, I don't know, around this saturation, then you're not going to be able to see the water anymore. So it will kind of look the same, but physically it's different because it has a different saturation. If we keep on forcing the NAPL into the system and then stop at this point here, and then begin to reduce the pressure, then we descend down a different curve. We descend down this imbibition curve. Call it imbibition because it's imbibing, just like you're drinking in your bar, imbibing water. Might not be drinking water in a bar, but of course beer is 90% water, even high-test beers. So you'll be imbibing water, and you end up at this irreducible saturation. We talked about two important quantities. They were irreducible saturations of water and irreducible saturations of the NAPL. The irreducible saturation, this would be SW0. This is the irreducible saturation, 0, of the wetting fluid, and that would be something like 20%. And this would be the irreducible saturation of the non-wetting fluid. So this says no matter how we try, we can't get this completely full of NAPL. We're always going to have a small amount of water because the water is coating the grains, and it's also present at these toruses or these donuts around the grain-to-grain contacts, our so-called pendular saturation, if you remember. And so this is an important curve for us that we'll now use. We're going to use this curve to say something about when the falling DNAPL will stop, and so we can use it for that. The other thing is that we can parameterize this curve not just in terms of a Capri pressure, which is the difference between these two pressures across the interface, but also in terms of what we'll call a J function. It's not equal to the Capri pressure, but we could take this curve in terms of Capri pressures, and we could divide all the ordinates of this by the interfacial tension and multiply it by the square root of permeability and divided by porosity. So in other words, take this Capri pressure, which we have here, multiply by the constant, that whatever this is for that particular rock, which has a permeability and a porosity, and the fluid, which has an interfacial tension. And we'd end up with a curve that looks exactly the same, but it would have different numerical values along this. And our use of doing that is because we know that the other important feature we've talked about is we've talked about a bubbling pressure. And the bubbling pressure is the pressure that we have to apply in the DNAPL on the outside so that a single bubble of that red fluid will break into the water-filled pore space in the biggest pore throat that's available. And then progressively, as you increase the pressure, it will fill up the smaller and smaller pore spaces. But this is important because this says when the first bubble of that invasion occurs. And we know that this value at PC0 is something like 0.3. If you remember from last time. The magnitude of this elevation in terms of the J function was equal to about 0.3. So that means that we know when the bubble will invade at this magnitude, and if we know the interfacial tension of the fluid which we're pushing into it, if we know the permeability and porosity of the porous medium we're pushing it into, we can immediately calculate what this pressure is that we have to apply. This is essentially your second assignment, and so that's the concept that you use there. And so what we're going to try and do is we'll use this curve, and especially we'll use this value of the bubbling pressure to be able to figure out exactly what pressure we have to, what height of fluid might we want to have on the surface in a 55-gallon drum of stuff before it's going to invade. Is it always going to invade? Or does it have to be a special height, which we could think of as being kind of H sub C? This isn't a Capri. This is a 55-gallon drum, 1.5 feet across, 4 feet high, and perhaps with Jimmy Hoffa in it. I'm not sure. If folklore is to be believed. And if it's filled with DNAPL and open at the bottom, what height do we have to have before something's going to move? We know that at some pressures, if the pressure isn't enough, nothing's going to happen. So at some stage, we're completely safe. But at some height, it's going to go in. So that's the question that I want to answer with you today. Okay? So that's kind of that's the recap, I suppose. And so if we go through this, and we'll come back to talk about this, remind me to come back to that figure later. All right, so this is the idea. Again, my horrible notes, but they make a point, I hope. This is our curve that we've talked about. It's a bubbling pressure here. This is pressure, Capri pressure on the vertical axis, which is by convention, the non-wetting pressure minus the wetting pressure. So that would be air, water in the vadose zone, or it would be NAPL, water, below the groundwater table, for those two different components. We know there's a drainage curve. We know there's a imbibition curve, and it looks a bit like this. Perhaps that's a bit more idealized than we would want. But the important ordinate on this is to realize that we have this finite pressure we have to apply before we invade the pore space at infinitesimal saturation, zero saturation essentially. This is zero saturation. Just to the left of this point is 0.01%, etc. So infinitesimal. And so we're going to be mindful of this. And of course, we can define this Capri pressure as some height of fluid multiplied by its unit weight. You know that. And so let's consider two cases. We can think of the first case, which is the salad dressing. So oil and vinegar. Vinegar, acetic acid, mainly water. Oil, lighter than water, sits on top. The question is, actually you probably got posed this question in 303. Can a denser fluid sit on top of a less dense fluid? Did we ask that question? What was the answer? Don't look at your feet. Actually, you're staring me in the face. That's good. Well, the answer could be either. And so the answer is that you never see that. There's no physical reason why a more dense fluid can't sit on top of a less dense fluid. And that's because the pressure acting on this interface would be exactly the same for each of those fluids, because you have the weight of the upper fluid, which is more dense, and the weight of that dense applied onto the lower surface is exactly the same to be in equilibrium at this surface. But if this surface makes a very small deviation from that by having a perturbation, then it will look like this. And now the pressure acting on this will be equal to this height plus a small change in height. But the pressure acting upwards at this point is just going to be equal to this height here plus delta H here. But this delta H is in the fluid which is less dense. And so if we look at this magnitude, then we have to account for the fact that the pressure acting downwards is less than the pressure acting upwards, right? Because the pressure acting downwards is this amount of the upper fluid plus this amount of the less dense fluid, while this is this amount of the upper fluid plus this amount of the upper fluid in addition. So this pressure, just by inspection, has to be larger in the red side than it is on the blue side. And so by definition, if the pressure acting downwards is more than that acting upwards, it's going to move downwards. It's going to move downwards, it's going to be more out of balance, and it will just keep on going. And so it will rearrange itself, so it turns itself upside down. So if it was a finite container, you'd end up with the red fluid on the bottom and the blue fluid on top. So either answer could have been right as to whether you can. So in practical sense, because of the fact that you'll develop this little perturbation, no matter how small, and it will grow, you cannot have a denser fluid sitting on top of a lighter fluid. It will penetrate down just like an inverse lava lamp. So that means then we could think about the same thing for a porous medium. Now this fluid that's acting below us is a porous medium, which is filled with pore grains, and between those grains it has pores. We know that in this porous medium it must behave exactly like this figure that we had on the top that I'll just draw again. Capri pressure versus saturation. And so it has to behave exactly like this. And we're interested in this bubbling pressure. We called it PB or PC0. And we said that it's equal to the height rise multiplied by the unit weight, say, of the non-wetting fluid. We've seen this before. And so now, if you do the same thing, the same kind of analysis as we kind of did here, then what do we have? We have the height of fluid, which is equal to this. So clearly it has a pressure that's applying at this base, which is non-zero. But we also know from our fluid mechanics class that any horizontal from as you go horizontally within a fluid, from this point to this point here, the pressure doesn't change. We're going horizontally, we're not changing elevation, so dP dz is 0, so the pressure at both of these points have to be the same. And so if there's a weight of fluid that's acting downwards, which is finite, and then this pressure acting upwards is 0, atmospheric we can take as 0, then this will fall. It'll fall down through it and keep on going. But that's not quite our system. That would be the case if this was a swimming pool and this was a can sitting on top of the swimming pool, held on top of the swimming pool. But this is actually a porous medium. And so we know the porous medium behaves like this, and so we have to overcome this pressure for this to go in. So quite simply, the pressure that we have, the height of fluid we can support, is going to be equal to whatever the bubbling pressure is. Simple. So that's the case for this particular case. So if you have a drum sitting on the top, it'll go into the subsurface like that. I suppose you could imagine that it would make what we will call a ganglion. So it'll make a little pulse that goes into the ground like this. So now again, if you go down through this, the pressure acting upwards at this point here, whoops, I wanted it to be blue. The pressure acting here is going to be this height multiplied by unit weight of water. And the pressure acting downwards is going to be this height, which I'll call H2, again multiplying by the unit weight of the non-wetting fluid. Non-wetting fluid is denser than the water, and so by definition the mismatch in the pressures here must be even larger than they were for entry. And so the idea is that there's nothing going to stop it, it's just going to keep on going as long as this supply is here to feed it, basically. So, that's the question. So we can calculate the height of material we need on the surface to be able to do that, and it's just given by this amount here. Simple equation. If we, okay, well I guess that's the analysis here. You don't, it's slightly different analysis. Well, this is the analysis of when it would stop. So if you have this material in here and you have a point and you again look at the interface between these, the red fluid, which is denser than the water, it's a continuous column, so the pressure just changes like being in a swimming pool of NAPL. The pressure in the water on the outside of this changes as the continuous fluid, as the height of this fluid multiplied by the density of the water. And to be able to enter across this barrier, you have to add the magnitude of the Capri pressure. So you can just do a force balance at this point in terms of the height of the non-wetting fluid. So this is the red one. And the blue one resisting it is everything on the right-hand side. So this is the height of the blue fluid to this same point. They're both at the same height, right? This and this are the same height. One is in the denser fluid, one is in the less dense fluid. And you have to add on to that a component which acts for this feature here. this entry pressure. It has to overcome this entry pressure, otherwise it can't go on. And so if you rearrange that to find out what the minimum height is that you have to have, it turns out that it's the entry pressure divided by 1 minus the ratio of the densities. And this is slightly different from the previous one. So we have two expressions now. We have this minimum pressure being equal to HC minus this. And from the previous one, if I scroll up, we have what is it, pressure? HC is equal to so we have two expressions. And so clearly those expressions aren't the same. They kind of look a little bit the same, but they're not. And so the question is, what's the difference between those? And the answer to that is that the difference is that they relate to the buoyancy. And so in the first example we dealt with, the bottom one, is we have the drum sitting on the surface, it's air outside, so the pressure at this point is atmospheric, and therefore this simple expression defines the behavior just by the force balance. But now what happens if we extend the porous medium up to this point? So this is now replaced with porous medium, which is a bit like the second example we looked at, right? A bit like this. So the ganglion is present within the porous medium. Well, what's different now is that the water level, instead of being down here, is up at the top. So the effective weight that the red fluid works down with is equal to its weight, but minus the buoyancy due to the water around it. So they are physically different systems. And so because you have buoyancy, making it less able to penetrate the subsurface, the equation ends up being different, and you have to overcome with a higher pressure to be able to get it to enter into the system. So this, I guess, PC0 over gamma NW is just HC. I guess probably this is the easiest way to think about them. And this is HC divided by something, a number which must be less than 1. 1 minus a density which is smaller than a larger density. So this has to be less than 1. And so this has to be non-zero and less than 1. And so if you divide this through by a number less than 1 that's non-zero, then this ends up being a larger number on the left-hand side. So the second ramification of this equation on the right-hand side is that if you want to answer the question, if you can start this and you can work out what critical height you have to be able to get it into the system, we know how to do that. We need a material property, which is this bubbling pressure. And of course we get that if we use the J function is equal to 0.3, which is equal to PC over interfacial tension times permeability over porosity square root. So that's kind of a useful equation for us. We know this at this particular point here, right? We know it's equal to 0.3 at this point here. And so if we measure the permeability of the soil, easy to do. Measure its porosity, easy to do. Know the interfacial tension of the fluid that's invading, easy to do. Go to the library. We can calculate really what the real Capri pressure is. And therefore, if we know what the real Capri pressure is, we know how high that height has to be. And permeability would be a common number to know. So the second question is, what stops it? So clearly, if we do the calculation and find out that this is able to penetrate to get to this depth here, what happens if there's no more supply from the surface and there has nothing to replenish this? What's going to happen to it? Well, there's nothing stopping it going down at the top, at the bottom, so it would move down, and it would just pull the top down with it. So the difference in pressure between this point here and this point here is really no difference from what it is here, and so we just physically translate and keep on going and going and going. And so as long as it didn't come up against some kind of Capri barrier, it wouldn't stop. The only thing that you could imagine would stop it, I guess you could think of two things. One is if it necks into two different parts. So if for some reason it necks into two different ganglia, and now individually these ganglia are less than the total number which allowed it to go, then it might stop. Or it might hit a Capri barrier, as we talked about here. And if it hits a Capri barrier, it may stay in this configuration, or it may be that it keeps on going and just ponds at this point above this Capri barrier, just as we saw in those earlier figures. So that's kind of the rationale of what we're doing. So the important equations to come out of this are we can get a minimum height that we have to overcome before it will move. Once it gets that minimum height, it will keep on going forever, unless it either hits a Capri barrier, which typically means that the permeability would be smaller, and therefore this term would be smaller and it would stop. But although the permeability is smaller, really the mechanism by which it's stopping is not permeability, it's by capillary entry pressures, which happen if the pore spaces are smaller to make the permeability smaller. It also makes the entry pressures higher because the pore spaces are smaller. And I guess I said it, we know what happens. It'll only stop going if it either necks down and breaks into two parts or hits that Capri barrier. So that's it. So that's our use of those curves. And I think that's kind of explained there. And the other stuff we talked about before. Yeah, okay. We're not going to stop yet. You're not that lucky, I'm afraid. So in terms of things that we want to talk about, so we put it in the big picture. So I guess actually it might be worthwhile going back to the big picture because I thought that was a useful slide. I don't know if it reorders them in. This is the slide we used before. So this is the big picture. We'd like to understand something about whether it ever stops, and if it doesn't, what are the controls on it. So we can now understand something about the architecture for this. We have to realize that in this Capri pressure versus saturation diagram, we're really talking about an REV. And so I suppose the REV here would be this purple box, which is included in one part of material that all has the same color. This would all have the same saturation of NAPL and the same saturation of water. Maybe the NAPL is 30% and the water is 70%. Maybe down here it's the opposite. The NAPL is 70 and the water is 30. But we deal with a continuum in this. And so if we want to understand how this stuff works, we look to apply the behavior around this REV, as we call it. And so that's kind of what we're doing. And so we understand something about the architecture. We also made the point that we can define this behavior for any two fluids. So we defined the Capri pressure in terms of the difference in pressure between two fluids. And we said for the fluids that we're looking at, this Capri pressure for the non-wetting fluid could be air in the vadose zone, or the pressure in the air minus the pressure in the water. So I guess that would refer to this bead pack, which is kind of water-filled, but at some stage as you go further up, it would be air-filled. Whoops, I didn't mean to do that. Didn't even know what I did then, actually. And the other option we have is if we look at the NAPL system, it would be the pressure in the non-aqueous phase liquid minus the pressure again in the water. So we can look generically at any two systems that include two fluids and are different. And so that's what we'd like to do. So let's go back to the other point I was just about to make. And this is also kind of a key slide, one that's in your notes, of course, this time. And it's this. So it's immediately before Capri behavior if you're trying to follow your notes, and I'm jumping all over the place. And so this is how we can think of that system in terms of quantifying it. So let's look at, in this case on the left-hand side, this is the surface of a field. This is the field going down. This is where the water table is within the field. Above the water table we have this vadose zone, or the Capri saturated zone as it's sometimes called, the Capri fringe as it's sometimes referred to. And this aligns directly with the shape of our Capri pressure versus saturation curve. This is the same curve we've looked at before. 0 water saturation to 100% water saturation. A Capri pressure. In this case, since it's in the vadose zone, we have the system is air and water. Right? Above the water table, it's mainly air, and there's a little bit of water. As you get to the tension saturated zone, it's almost all water with a bit of air, and below the water table it should be 100% water and no air. And so if we look at what the pressures would be in these zones, we have to think about what we what we understand in terms of pressures. So we know by definition that the water table is where the groundwater pressure is atmospheric. So if we draw a pressure versus depth diagram, as we've done many times in 303 for instance, which is this, then we know that if you did that in a swimming pool, the pressure versus depth diagram for water would look like this. Pressure at depth is equal to the unit weight multiplied by the depth below whatever the datum. We're choosing the datum where the pressure is equal to 0, because we'll take atmospheric as 0. Even though you think it shouldn't be 0 here, it has to be by definition. That's what the definition of the water table is. And so as you go down, the pressure differential looks like this. Right? The gradient of this curve is given by 1 over the unit weight of water. So it's quite steep, quite flat. If you went down from this point and instead of this being filled with water, it was filled with air, the pressure from this point would build at the unit weight of air. The unit weight of air from that point will build like this. We know that air is a kilogram per cubic meter, water is 1,000 kilograms per cubic meter. The gradient of this should be 1,000 times less than this, so it will almost be along the axis, but be slight. And that would be the magnitude of the Capri pressure. That would be the air pressure if it was air-filled, just based on the heights. So let's go in the opposite direction. If we take the water and we go above it from this point, the pressure change in the water is just, it varies according to the unit weight. And so that means as you go up this amount here, the pressure at this point has to be this magnitude. This will be the pressure in the water. And the pressure in the water is going to be equal to the unit weight of water times that elevation. So let's say this is Z1. Right? Seems kind of strange, but it's in tension. It's probably not in enough tension to cavitate, to turn into vapor, hopefully, otherwise it would cavitate. And if you do the same for the air, going up, then you end up with this. And the pressure of the air at this point is going to be, is equal to the same elevation multiplied by the unit weight of air. Almost zero. 1,000 times less than this. And importantly, the difference between these, I don't know if I can draw it, it's too sharp. If you subtract away the pressure of the air from the pressure of the water, that by definition is the Capri pressure. And so if you think about it, at this point, the pressures are equal. The difference between those pressures is zero, and the Capri pressure would be zero. As you go up a height z, the pressure at this point would be the Capri pressure, and the Capri pressure would be equal to the pressure in the non-wetting fluid air minus the pressure in the wetting fluid, which is gamma water, which I guess you could write as Z1, including those things together. Unit weight of water is larger than this, so this would be a negative 1,000, 10, it would be a negative 10 kilonewtons per meter cubed for the unit weights, multiplied by a number. Z1 here is 0, so the number is 0. Z1 here is a number that's finite, so it would be larger. If you go up twice as high to Z2, then the pressure would be twice as high. So all to make the point that the Capri pressure scales directly, is proportional to the elevation. That's all. That's all the point I'm making. It scales linearly. You double the height, you double the Capri pressure from this origin. And so that means that if these are the Capri pressures that are going up an elevation as you go up in the system, then perhaps you could fit the Capri pressure versus saturation curve so it fits at the right ordinate. This ordinate has 0 Capri pressure, but it's also 100% saturated, so it would be exactly this point here. And as you go up here, this just scales this diagram. That's all. So everything we've been doing has been to see how we get these diagrams and what these diagrams relate to. And so what this diagram says to us is that at this shallow elevation here, we are roughly, that's a bit of a blunt object, that one, we're 95% saturated with water, and correspondingly we are 5% is a saturation of the non-wetting fluid, the NAPL. And as we go up to this point here, which we double this, we would be, okay, text from my son, recorded for posterity here. So this would be the saturation of the non-wetting fluid, which it looks to me like it's about 70%. And the saturation for the less blunt object, wetting fluid, which is water, which is 30%. And so that kind of looks a bit like the chimney of NAPL going into a big red pool at the bottom, right? The chimney is almost all water, mainly water, maybe a smear of NAPL within the pore spaces. And so only 30% is NAPL. Happens to be air in this particular case, but the same principle. Well, let's go back to the Vado zone. So the non-wetting fluid is air, so it's mainly air saturated, and it's got a little bit of water as pendular saturation. As you get deeper down there, you get much more water, and you get much air because the air is squeezed out. And then you end up at this point here, which is really the bubbling pressure, which is the top of what we call the tension saturated zone. So that's all that we want these curves for. We want them to be able to say something about that. Okay? So that allows us to say something about how the saturation varies as we go up in height. And I guess the other useful thing for us to know something about is that the mass of fluid is going to be equal to the volume of the aquifer multiplied by the porosity multiplied by the saturation of the, say, the non-wetting fluid multiplied by the density of the non-wetting fluid. So the volume of the aquifer at a particular height, say, a little component of it. So the volume of the aquifer multiplied by porosity is the volume of the pore space, these two together. The volume of the pore space multiplied by the saturation is the volume of that fluid within that pore space. And multiplying that volume of the fluid times its density gives you its mass. And so that might be something that you might like to know if you're going to remediate the site, because you might like to know how much you have to take out of it. And it gives you a very easy way to do that. So that's one of our interests in all of this. So that's in using the Capri pressure versus saturation curve in the vadose zone, above the water table. So we could also do the opposite, and we could look at a system that instead of being air and water, now is NAPL and water. And so we're going to the groundwater table. So we're taking the groundwater surface here. And so we're saying that the water table is at the surface, no vadose zone. And we have a little ganglion of DNAPL, which is going in there, which is this green stuff. And we're going to do the same analysis as before. And so if we take the green material, we know that from zero pressure as we go down here, the pressure at any point will vary with the unit weight. So this here will be the pressure of the NAPL at this point, where it would just be the elevation Z. So this would be unit weight of the NAPL times Z1. If you can't see that. Z1, that's what this is. If we go down in the subsurface only in the water to get to that point, this is here. The first one was here, and we're doing this here. Simply connected, so the pressure here has to be this. This pressure, by definition, has to be the pressure in the water, which equals the unit weight of the water times Z1 at this point. And we can define the Capri pressure as being equal the pressure in the non-wetting fluid minus the pressure in the wetting fluid, the water. And we could write this out, I guess, in terms of, it's going to be Z1 multiplied by the unit weight of the non-wetting minus unit weight of the wetting. If it's a DNAPL, the non-wetting fluid is always denser than the water, by definition, dense non-aqueous phase liquids. This is always going to be positive. This is going to be a constant. It's multiplied by a depth, which means that at this point here, the Capri pressure is 0. And of course, Capri pressure increases as you go down this graph. So this is our Capri pressure versus saturation curve, just flipped over upside down. So the Capri pressure is 0, and we know it's potentially 100% saturated with water. As we go down here, if we go down to Z1, then we know that of these, am I doing this the right way? No, I'm not. We know that this is the saturation of water. What do you think? 60%? This is the saturation of NAPL. Originally it was 0 when we were trying to push it into the ground, but now it's equal to 40%. Of the non-wetting fluid. And as we go down here, if we double, if this is Z1, if this is 2, Z1, whoops. Oh, didn't mean to do that. I meant to do this. And so in other words, at this stage here, it's changed. So this is the saturation of the non-wetting fluid, which looks to me like it's 70%. And I'm really enjoying my colors today. It's like a crayoning session. Saturation of the water, which is about 30%. Remember, these two have to add up to 100%. If it had air in it, I guess they don't. All of the components have to end up. We've only talked about two components: vadose zone, air, water; saturated zone, DNAPL, water. But it could also have air in different places. So there could be more than two fluids in the system. And so that also says something about what we think of, right? So that means high up in the column, it's mainly water above this. And as we get further down, it's mainly DNAPL with a little bit of water. And so what that starts looking like, I suppose, if again we go back to that figure, actually we won't go back to the same one, but you see a similar thing of that, a different slide talking about something else, but you see the same thing here, right? Up here, if you look in here, it's mainly water and a smear of DNAPL left within us. As you go down here, it's almost completely DNAPL, and there must be some residual water in there because it hasn't been squeezed out. That's it. That's it. So that's what we're attempting to do. And yeah, so the last thing we were going to talk about was saturation versus depth distribution. And so that's exactly what we have on that previous slide. So that's it. So I think this is a key figure. It kind of explains exactly what we're trying to do. You'll get a chance to try this for yourself in due course, but that's the deal. 55 minutes. This must be a regular Monday, Wednesday, Friday class if we're only 55 minutes. I don't have anything more to say. So we've gone through everything in our list. Next time, I don't know, we'll talk about, as he finds what we'll talk about. We'll talk about the motion. So everything we've talked about so far has been getting this fluid in and then it being static. So the equilibrium saturation under given pressure. So that's how we can say the aquifer will look like after a couple of months, after this stuff's been dropped in and it's kind of rearranged itself and it's reached an equilibrium and it's essentially held by the interfacial forces. That's the only thing that controls its behavior. But in getting to that equilibrium, how quickly it gets there, or how quickly you suck it out by removing it or trying to remove it, is controlled by different processes. And so the next thing we'll talk about is we'll talk about multiphase flow. And I suppose that relates, if we come back to these figures, if they should still be playing in the background. They are still playing in the background. So if you look at this figure on the left, then physically what's going on is this is flowing, right? Two fluids are flowing through it. And so the rates at which these fluids go through this says something about how quickly it will arrive in this set architecture, which is controlled by interfacial tension and Capri behavior only. But getting there is controlled by some other coefficients, namely permeability. And also, this permeability is potentially controlled by the fact that there are two fluids flowing at the same time. You might have water flowing, you must have water flowing, right? If you have a pore space that DNAPL is going into, the pore space only has a finite volume, and so what's coming in as DNAPL must be going out as water. They're replacing each other. And so those two fluids must both have velocities at the same time, and could conceivably have similar velocities, different velocities in the same pore, But what we'd like to do is we'd like to represent this REV, an equivalent volume that contains a lot of these grains and a lot of pore throats, and we'll look at trying to figure out what the permeability is that describes the flow of fluid A and fluid B. The flow of water and air in the vadose zone, and the flow of DNAPL and water in the saturated zone, because they say something about how quickly it gets into place. We might be interested in that. And we'd certainly be interested in that if we want to suck it out in some kind of remediation method. So that's the background we'll deal with there. So that's it.